Hello, everyone. Welcome you all. I want to introduce myself first. I am your host tonight. I am Mehmet Emre Astarcıoğlu. Tonight, we will host our professor, Dr. Süreyya Akgüz. He will give her speech on machine learning and optimization for ML. She is academician at Department of Mathematics of Bahçeşehir University. Without further ado, I want to give speech to Professor. You may start your speech, Professor, when you feel ready.
Thank you. Okay, thank you very much. As Emre introduced me, I'm working at Department of Mathematics. I'm also head of the department. So since from my PhD, I'm working on machine learning and also optimization. So as you see from the title, I wrote there, machine learning needs optimization. Actually, machine learning itself is under the umbrella of statistical learning. So it consists of different disciplinaries: statistics, mathematics, operations research either. So today I will talk about recent optimization models in kernel learning. So kernel learning appears under, again, machine learning and deep learning and some applications. I will start with my multidisciplinary projects for a startup. Here I'm also running my computer vision lab. So in engineering department, in the Faculty of Engineering and Natural Science, I'm the coordinator, director of the computer vision lab. So in that lab, there are other instructors as well, other professors. They study together with their students, and these are my recent PhD students. And I have one alumni, Pınar Karadayı. She is now working in Arel University. She's head of Department of Computer Engineering and also Electronics Engineering. So I have now one graduated student, and the others are ongoing students. So with those students, with some others as well, I didn't list all of my students, but just I gave you the recent ones. We finished such projects. The one on the left you see is on predicting diet treatment. So this is on health. So we used machine learning techniques in order to understand when person lose weight. Is there something happen on the brain, or just does he lose weight physically? Is there something going on the brain waves? So we measured the brain waves through this EEG, electroencephalography, it's called. So there are some electrodes sticked on your scalp. So you measure the potential, electrical potentials. So we showed some food images versus non-food images, food versus non-food verse, and we understand through the diet process, before diet, in the middle of the diet, and after the diet, what's going on. And we analyze the data that we collected from this EEG measurements by machine learning algorithm. And this is completed project. We published the paper, and one more paper is on the process. Another one is an ongoing project. It's going to finish in September. It is more on computer science. So rather than application like this, like in health, this is to develop deep neural networks. This is to develop neural networks using optimization. And here there's a specific name for this optimization called sparse second order conic programming. This is one of the subfields of second order conic programming, is the one of the subfield of optimization. So here basically we collect ensemble of deep neural networks, but in our project we used image data sets like CFAR 10, CFAR 100. Maybe you are aware of these data sets. These are the famous data sets to validate your algorithm. And mostly CNN algorithms, convolutional neural networks, are used in these algorithms. And we created different architectures, some diverse architectures, accurate architectures, and we construct a pool of architectures, and we want to learn which of these architectures are useful to predict my unknown data points for my data set. So that's why it's called pruning. So we prune the ensemble, the pool. So we select the most useful ones among those architectures. We select the subset, and then we predict the unseen data point using aggregated neural network decisions. Aggregation is simply can be voting. You can vote among the community, like voting in elections. So you have different architectures and you voted. I don't want to go more in detail. If you are curious about this, you can always communicate with me. You can always send me email. And another interesting study is on understanding creativity. This is the creativity of a person, of a human, by, again, EEG analysis after and before training program. This training is creativity training program using machine learning methods. So we collected the data from companies, some companies administration, some from HR department, different people. We gave one of the person trainer who is specialized on creativity trainings, gave the training for 9 weeks, and we measured EEG before, in the middle, and after, and we checked before and after if there's any change, and we analyzed the data again using machine learning. So I wanted to start with such a soft introduction with some interesting applications of deep learning, of machine learning, and also optimization, as I told in the second project. There are also others, so I skipped this outline here. Actually, I removed, where is it? I removed the third part. It was too long. So if there's anybody who is not aware of machine learning, or who is not familiar with machine learning, I want to start with a soft introduction. Machine learning is everywhere now. You already heard AI everywhere, from your cellular phones, in Amazon, in the recommender systems, on e-commerce, everywhere. So there are some examples of these. This is from Amazon. For example, it gives you, it recommends you some films according to your selections, according to movies that you watched before. So this recommender systems actually is based on machine learning. Another example is driving. So there are driving. Actually, this is not self-driving. This is an old example. This example is based on drowsiness. So when you are sleepy, when you are drowsiness, there's a drowsiness prediction of this car. So when you are sleepy, it gives a warning. So you may know these properties of some cars. Also, there are self-driving cars. You know this. So all of these are some examples on machine learning and AI. Also, another one is detecting spam or regular emails. Of course, face recognition, right? Facial expression classification. So in the example that I gave you in the car, in detecting drowsiness for during driving, is based on facial expression classification, because from the video, from your facial image, it detects if you are drowsy, if you are tired, if you are sleepy. So facial expression classification is another example. In gamings, you know this, in mobiles, so credit cards, for example, credit card risk, or recommending different credits. I have master students who are working on different areas. One of my students working on churn prediction on banking, for example. Churn means if the customer will leave the company, let's say, the customer will leave the banking or not. Or churn can appear on business, in marketing, in business analytics. You are a customer, so for example, if you are a customer and you go regularly shopping in some market, and suddenly you stopped shopping there, that means you are churn. Okay, so there are different examples in real life, and this is from biomedical studies. So this is the brain image. You detect some cancerous cells, some tumors, and you here you visualize the functioning of the brain. And this is automated by machine learning, by AI techniques. So the question is, how can we tell machine learn can? Right? So I pictured here is the robot. So can robot read and understand? What do people learn? How do people learn? So we learn from experience, right? So when you are a baby, your mother, your father told you everything, you listened and learned. And from the experience, you learned. So AI-based systems learn from data. So you should give some data, labeled or unlabeled. So it learns from data and then it follows the instructions, right? This is another pictures of how does it work. The computer learns to recognize patterns in historical data. So it learns the pattern, it learns and it understands, it finds a pattern. You can call it pattern recognition. So you give some historical data, for example, in time series analysis. You give some time series data, it recognize the pattern, and then it predicts, for example, in stock exchange, stock rates, predicting stock rates, and predicting exchange rates. So you give the machine some historical data, it understands the patterns, and it predicts exchange rate. One of my students studied to predict exchange rate from Twitter data, for example. It is natural language processing field. So the learned machine then looks for learned patterns, as I said, and when it encounters a familiar pattern, same pattern, it predicts likely future developments. We can partition, basically, machine learning as supervised learning and unsupervised learning. In supervised learning, we can subdivide it as classification and regression, where in the classification, the output, the outcome of the data is categorical output, because you categorize it into classes. But in regression, you predict it is continuous values, like house prices or some gene expression profiles, some gene expression patterns. Okay, so it's continuous values. But in classification, it is categorized. In unsupervised learning, there is no outcome. You only have data. You don't know which data belongs to which class. So you do clustering. This is one of the examples of unsupervised learning. There is also one more, reinforcement learning. So it learns with giving awards and penalties. For example, when a kid touched to a hot glass, he or she understands that he feel a pain, so he doesn't do it again. So it's like this. So in reinforcement learning, the algorithm works with rewards and penalties. Let's start with supervised learning setup. In supervised learning, we have an input X from a set. So it can be, this is in general, I wrote here X. So it's generally from Rn, okay, so it is multidimensional vector. Here it is just 2, you see just 2. Vector of features, so this X, the component of this vector, this multidimensional vector, composed of features of the data. Those features describes the data. So when you collect the data, you collect the most important properties that can describe, that can make the link, the relation between input and the output. So the input is here X, the output is the target. In regression, we call it response, the output, okay? We call this T, the output. You can also call it Y, and sometimes it's called Y, mostly it's Y. And our objective is find a mapping, find a function, find a mapping between X, between the inputs and the outputs. So how can I fit this data using some function, using some graph? What is the graph of the function that fits to this data? This is my main question. Based on, of course, some given data. These are my given data. Very simple example on linear regression. So we have a data set, inputs and the response. And I will use these data set as a training in order to approximate the function which makes the relation between my inputs and outputs. This is simply in 2 dimension, it is a line. In higher dimension, we call it a hyperplane, and this is the equation of the hyperplane. Okay? In higher dimension, it looks like a hyperplane. The WT is the coefficients, it's the normal vector of the hyperplane times x plus the intercept term. This is the intercept term. But how I can find the best line? I can also draw it like this or draw it like this. So how can I find the best one? Here, the optimization comes into play. So I want to find the best refers the minimum loss, the minimum error function. A loss function, first of all, let's define. The loss function defines how bad it is. If, for example, X, the algorithm predicts Y. Now, if my algorithm predicts Y, and if T is the correct value, the actual value, this difference gives me the error. So if I minimize this loss function, I get the best model, I get the best parameters, and this W becomes my parameter. This is the unknown. If I know this, I can draw the line. I can find the best line. So from this minimization, from this optimization problem, I can calculate the best parameters, W's, to find the best line. I will not go into detail of how we find it. This is sometimes called cost function or empirical or average loss. Okay, the empirical loss. Because why is empirical? Because my loss is based on given points. I minimize the empirical loss on the training set to find the best fit. So we define the cost function. This is the also loss function. Okay. So in deep learning, you can maybe if you are familiar, this loss function appears a lot. There are commonly two commonly applied mathematical approaches for this to find it. From the calculus, you can find smooth function, you can find critical points, and you equate derivative equals 0. You know this from calculus. But in the multivariate generalization, this is equivalent to gradient vector. Okay? So, solution may be direct or iterative. When you solve this, when you minimize the loss function, okay, you convert, you approximate to the solution. So if you equate the gradient to 0 and solve it in a closed form, this is a direct solution. If you apply optimization techniques that iteratively gets closer to the solution, okay, so this is iterative way. So the optimization techniques starts with some initial guess, initial solution, and then iteratively updates the solution in order to converge to the real solution, the optimal one, gets closer to the solution. There is another example for classification. Here's the classification problem. It's the famous one in 90s. My PhD was on the support vector machine. In support vector machine, it constructs set of hyperplanes in high dimensional or infinite dimensional space. Here in the picture you see two class of points, blue class and red class. I want to separate as best as possible these two class using this linear function. It's an hyperplane. As you see, it's the same equation, wx, it was plus b or minus b, it doesn't matter, okay? So I have this hyperplane. And the question here that the optimization problem appears when you maximize the distance between 2 points, 2 classes, right? So you maximize the distance between 2 classes, and this maximization, this is the distance function. This is for the hinge loss, squared hinge loss, so these are technical details. So the basic idea is you maximize the distance. So we can see it like a tube, and these dotted lines refers to support lines. Okay, so in support in SVM, let me call it SVM. In SVM language, we call the point signs which are on this supporting lines called support vectors. Okay, so this maximization problem gives you optimization. My aim here is to show you where optimization appears in machine learning. There are some details on optimization part. We have primal problem, you drive dual problem using some Lagrangian function. This is more on optimization theory, so I will skip this. And we use also a regularization term together with SVM. So what does this regularization term does? It regularizes the complexity of the unknowns of the parameters. This regularization function can be L1 norm or L2 norm. So in mathematically, L1 norm is just the sum of the absolute of the variables. L2 norm is the squared one. Okay, and lambda here is the regularization constant. So I minimize the loss with respect to the unknowns W's and B's, because in my hyperplane, I have unknown W and B. That's why these unknowns appears. This is the optimization problem. When you solve this optimization problem, you will achieve the best line. Okay, I think I gave the main intuition. There are some versions, the hard margin, you don't allow any misclassified points or you don't allow some points into this tube. In soft margin, you allow some other points in the tube. Okay, so you regularize here with some error constants. You add to your objective function some error constants to mimic this, to regularize this. And this is the constraints of your problem. So I will not go into these mathematics inside. So when you allow the soft margin problem, you define some variable, and this variable tunes how far you allow this point that go into the other side or be in the side. If it is 0, it is on this supporting plane. If it is less than 1, this point goes to the wrong side, because I discriminate these two group of data with this hyperplane, and this point went to the wrong side. Similarly, this point also went to the other side. Okay, it's the slack error. Look here, when it is greater than 1. Okay, this is the general looking of how SVM looks like. We minimize this, it comes into play maximizing this distance. The distance formula is 1 over W. It corresponds to minimizing W and so on. These are some technical details, okay? Let me skip this. There is another classification method called logistic regression. In logistic regression, there's a probability equation here, let's say. Okay, there's a logistic submate function, and it gives you such curve. And on the output, whenever you give the data X your input, you obtain probability values. And if you put some threshold, you can say, okay, if it is greater than 0.5, it is on one class. If it is less than 0.5, it's on another class. In logistic regression, there's also loss function. You can also add, again, regularization term, and it turns into a minimization problem. Okay, you minimize the loss because here you don't know W. Here in k-nearest, there is no the formula. In k-nearest neighbor, you look at the weight, you look at the majority voting of the unseen point. If it is, this k means the number of points in the neighborhood of the unknown point. For example, if I want to classify the screen, this is the unknown point. If I want to classify it, I just look at the, if it is 3 nearest neighbor, I look at the nearest points to this unknown point, and I look at their labels because I am given training data. And it seems that this is blue. I have just one blue. I have just 2 triangle, red triangle. And when I do voting, the most frequent, which class has the most number of points inside this circle? These 2 triangles. So I assign the label, this red one, as red triangle. If I increase the k like this, okay, this dotted ones, if I ask the same question, when I do the voting, I will get different answer. I will get the answer blue square, because blue square has more points than triangles. It's 3 versus 2. Okay. There is another method, LDA, the linear discriminant analysis. This is the discriminant function. Here, some technical details. This sigma sum is the covariance matrix. So, of course, I will not go into detail. Here in linear discriminant analysis, this is also supervised learning. You discriminate the classes using linear function, linear boundaries. Let me see the picture. Yes, here, for example, this is the linear boundary. Okay, you have 2 groups of data, and according to this discriminant score, there's a discriminant score function. You calculate the score and you get the prediction. There is another issue called model selection. So how do I choose the hyperparameters in the model? In my loss function, for example, remember, let's go back to this regularization term. Do I know the value of lambda when I minimize this? I don't know. So it is my hyperparameter. So which parameter, which lambda is best before I solve the problem? So that should be determined before training the model. So model selection refers to the process of choosing the model that best generalizes my dataset. For this, there are methods like cross-validation. So we have training and validation sets to simulate unseen data. Of course, overfitting happens. Overfitting means you have a good error on training, but very bad error on validation. That means overfitting. It performs well on your training, but it cannot generalize. It generalizes poorly means your test error is bad. Underfitting may happen when your model performs poorly on both training and unseen data. So we use cross-validation technique. So basically, cross-validation is splitting the data into k-fold. This is called k-fold cross-validation. 1 fold, 2nd fold, 3rd fold, and so on, k-th fold. And you take one portion, 1 fold, for testing, for validating, and you use the rest for training to build your model, to construct your model, and then you evaluate your performance of your model on that test set. And you repeat this process from 1 to k. On the second iteration, you choose this as a test and you choose first, third, fourth, and so on for training. You repeat until k separate folds are chosen, k independent folds are chosen as a validation set. There is another type of cross-validation called leave one out. So leave one out is just leave one point for validation out. You leave this point out of the training and you consider n-1 points for training and 1 point for validation. And you repeat this procedure n times. Okay, your model is trained for n times. You can guess how it's time consuming. An important issue, as I already mentioned in regularization in this regression or in and also in minimization of the loss functions in other methods, this regularization term is applied to objective function. So this is to regularize the complexity of the model. And here lambda is the real hyperparameter that controls this regularization function. It's the regularization coefficient. If I choose this regularization function L1, it looks like this. This is my loss function, and I find my objective function. I find the optimal on this corners. If I choose L2, I can find some anywhere, right? So what do I understand from these pictures? L1 looks sparse. Sparsity is one of the important problems in machine learning. If I want a sparse solution, then I should definitely use L1 norm. It's one of the mostly used regularization function in machine learning. Sparsity plays important role in machine learning. When you compress image, in image compressing problems, you need sparsity, right? If sparse means, by the way, if you don't know, let me define. Sparsity is sparse vector means I have many zeros. The non-zero elements are few. That is sparsity. So if I want to have sparse solution, I have many zeros or many values close to zero. So non-zero values are few. So what does this help me? Sparsity helps me in running time of the algorithm. Right? It's not costing. And for example, in feature selection problems, if I find sparse coefficients for redundant features, that helps me. You may know lasso regularization, lasso regression, rich regression. Rich regression use L2, lasso regression use L1. So you can use lasso regression to decide which features are important, which features are not important in your dataset. I just said this here. Lasso penalized this. It used this regularization term. Rich regression used this term. So it came to unsupervised learning. So in unsupervised learning, I want to categorize or group the data. Okay, I want to group the data according to their similarities. I don't have any outcome here. In supervised learning, I have outcome. So somebody tells me this is apple, this is orange. But here nobody tells me anything. Everything is round shape. I don't know which one is apple, which one is orange. If I don't know, if I'm not taught in my life which is apple, which is orange, so both of them looks like a round shape. But of course, its tissue is different. The orange tissue is different. Apple's tissue is different. So how do I discriminate the groups when I'm given many apples and oranges? I discriminate them by looking at the similarity of these apples, similarity of the oranges. So I observe from the similarity, apples are different than oranges. So I can discriminate these two groups of fruits. So I want to group data points that are close to each other, that are similar to each other. And the question here is how we define the similarity. So of course, it's just not image. There can be anything unsupervised. So I should define similarity in mathematical sense as a vector space. So in the vector space, each of these round shapes refers to a point in XYZ or Rn in coordinate system. Let's think about just XY coordinate system. If these are my apples and oranges, they refer to a point. They refer to a vector. So they have components. So I can define their similarities looking at the distances. As you see, they are close together. So I look at the distances. So the distance metrics can be used for similarity metric. Okay. Now let's define the centroid of the cluster. It is the point here, it's the centroid, it's the center, cluster center of the cluster. We call it this group, the cluster. And the centroid is computed as the mean of all the data points in the cluster. Okay, there are different types of clustering. So I listed here, I will not read. K-means is the one of the well-known. Quasi means, so this is overlapping clustering. Agglomerative clustering, this is hierarchical clustering. Divisive clustering from top down, bottom up approach. And let's see some examples, some applications. The first example, grouping people of similar size to get together to make small, medium, and large t-shirts. Right? You group the people. If tailor-made for each person, it will be too expensive. If one size fits all, then it doesn't fit all. So we need to categorize into different groups, small, medium, large. In example 2, in marketing, we can segment customers according to their similarities, according to their behaviors, according to their shoppings. Example 3, given a collection of text documents, we want to organize them according to their content similarities. Or collection of data from text documents, for example, the customer comments on e-commerce can be negative comments. You can group the data set, group the text documents according to customer comments. This was one of my students' study. So positive comments, neutral comments, negative comments, looking at the text documents. One of the well-known, as I said, clustering is K-means clustering. So in K-means clustering, K is the number of class that you need to give as a user. It's the user input. You should first define K, of course, that tells us it's an hyperparameter. So without knowing the labels, how can I decide the best K? The idea behind K-means is the clustering is that a good clustering is one for which the within cluster variation is small as possible. So we minimize within clustering variation. Okay, here again we have this minimization optimization problem. Okay, within clustering. Typically, this within clustering variance is it use Euclidean distance. Okay, this is the formula for within clustering variation. If you combine these 2, 2 and 3, this is just a mathematical derivation of this. You end up with this optimization problem. And if we look at the algorithm, it randomly assigns the number from 1 to k of the unknown points here in step 1. It randomly assigns. You are given such data. You don't know the colors. You don't know the groups. So it randomly assigns because you know, okay, let's say here there are how many colors? 1, 2, 3. There are 3 colors here. So you randomly assign those black points into random colors. And then you calculate the means of these colors. And then you update the points by looking at the closest distance. For example, this point is closer to the orange one rather than the pink one, so you reassign it as orange. And all these points are closer to the orange group. You see the orange group. So all these points are closer, so all these points are reassigned. When I look at these points, these are closer to the pink one and these are closer to the green one. And then you recalculate the centroid, the mean of these points. So these are the new means. And then you look at, again, if there are other points which are closer to the yellow, which are not yellow. So all the surroundings are already yellow. If there were pink, for example, I would reassign it to yellow. So I look at, again, the surroundings of green. So I see some of the points. Do you see this? These pink ones are closer to the green group rather than the pink one. So in the next iteration, I reassign this pink one to the green one. So you see the final result. These points became green. Now, I want to start with deep learning. I just give the brief introduction to machine learning with some well-known methods. I hope I didn't bore you. And for deep learning, I liked one of the presentation from MIT. So I will go on with their presentation. It's really simple and easy to understand. So this is the classification of the topics. As we are machine learning, we are doing machine learning, we are classifying. Here the topics are classified. Under the AI umbrella, we have machine learning. In AI, any technique that enables computers to mimic human behavior. So you can define it like this. But in machine learning, it's the ability to learn without explicitly being programmed. You program with some statistical learning, you use optimization. And in deep learning, actually it's under the machine learning. It evolves from neural networks. It extracts patterns from data using neural networks. Neural network is a method under machine learning. That's why deep learning is under machine learning. So actually it's not a new learning. It is just the evolved version of neural networks. So why nowadays people are mostly use deep learning. Everybody talks about deep learning. Whenever we send a paper, if we don't use deep learning, they always ask why we don't use state-of-the-art techniques, deep learning. Of course, in AI and machine learning, nobody says this is the best way. Sometimes the basic statistical methods outperform deep learning techniques. It happened to my master's student. He has a data set on marketing. It was time series data on sale forecasting of a mall, and he used statistical techniques, and statistical techniques outperformed one of the deep learning. It's called LSTM, long short-term memory LSTM. It beats it was very old method, that statistical methods. Anyway, so nobody say it's the best. Okay, in the machine learning, we cannot say this. Can we learn? For example, here you see that some images. Can we learn underlying features of these images? Here you see lines and edge. It is the low-level features. In mid-level features, so you add more levels to understand the picture. So you see some eyes, nose, and ears. If you have high-level features, you can see the faces enough. You can see the facial structure. So in deep learning, it's easier to extract high-level features. So here in this picture, it explains the history of how it evolves. In 50s, there was stochastic gradient descent. Actually, it is so the gradient descent, also known as in optimization steepest descent. So it's stochastic means it's stochasticity means it's the randomness. You can think it as a randomness. So the perceptrons are developed, and then in 90s there were SVMs, and with multi-layer perceptrons, neural networks are developed, and then afterwards deep convolutional neural networks. I think this DNNs are most started to be famous around 2007, 2009, 2010. So when you have a big data, you have larger data sets, okay? And it's easier collection. You need easier collection and storage. Also for hardware. You have GPUs, massively parallelizable. Now the technology developed. That is the reason why we can use these DNNs with these high-tech. Before there was no such strong GPUs, so it takes too much time. This running time, this training time was too long to get the result, to get the architecture. So these perceptrons are the structural building block of deep learning. These are the inputs. These are the features of the data. And we call these W's to be the weights, and we sum, and we use some nonlinear function to get the output. So mathematically, I take the linear combination of these inputs, x1 times w1 plus x2 times w2 plus xm times wm. So it's just from 1 to m. And then this function g is a nonlinear activation function. It's like a logit function. It's like a log function. And you decide the output. It gives you the class probabilities. It's like the logistic regression function, it looks like, right? So it gives you the outputs as the probabilities of the classes, and you have the output. In forward propagation, you have the term for the bias with the weight W0. It's for 1. You do the same. You have the bias term, okay? The rest is easy. Is the same. And there is vector matrix product form of this writing, okay? This summation can be written as this matrix vector product. I will not go to detail. So here is the example for activation function. You remember this equation from logistic regression, right? So you just substitute the inputs that you obtain from this sum into this function to get the output. If it's greater than 0.5, for example, you can assign it into the one class. If it's less than 0.5, you can assign it into the other class. There are other functions as well, common activation functions, sigmoid functions, the one that I showed you, hyperbolic tangent, rectified linear unit. This is very commonly used in CNNs, ReLU functions, and these are the functions, the libraries in TensorFlow. Okay. The purpose of activation function is to introduce nonlinearities into the network. Here you see that my data is nonlinear. It's not linearly separable. I cannot separate from here with a line. Non-separable. It's non-linearly separable. As you see, if I use activation function, something like this, I misclassify these green points. I misclassify these ones, right? So I need something nonlinear. If I use some nonlinear function, I can classify with this nonlinear function. This is not a line, right? It's nonlinear. This is one of the mathematical example that here you give the weights. Of course, we don't know the weights. This is for a given weights. We have this output, just easy substitution. So in real life, we don't know the weights. We find the best weights using optimization. We will see this later on. This is another one. For example, you take the inputs and you put it into the function. You get the output. And you classify it. If it's greater than, if it's less than 0.5, if it's greater than 0.5. So how do we build neural networks with perceptrons? This is the simplified version. So we have inputs, our features. So we have weights, our sigmoid functions or nonlinear unit function. So we have this, the simplified version. Okay, so it goes like this. We can have more than one unit. For this time, we should put here another index. So I will not go into these too much technical details. This is the code for this TensorFlow. So you define the layers. Here you see that we have 2 units. These are called units in the layer. This is my layer. So I define 2 units here. And this is called hidden layer. So here I have 1, 2, 3 to D1, whatever you give. And this is my final output. Okay, you take all the combinations of the sum, and all these linear combinations are weighted, are multiplied with the weights and go to these units. And then it goes with this function g, z1 is substituted on g, and it goes through here similarly. Okay, everything is combined. So it is the mathematical derivation of how does these units look like. I multiply x1, w1, 2. It's w1, 2 because 1 to 2. This is 1 to 1. This is 2 to 2. This is m to 2. Okay, these indices shows m is the input, and the second index is for the unit. In multi-output perceptron, okay, here in this picture, you see that we have n dense layers, 1, 2, n, and I have 2 layers here, right? So in deep neural network, you increase the layers. So let's see this. So there are other layers, okay? That's why we have these. That deep comes from the width of the network also. Okay, the width of the network is deep because you have more than you have many layers. How can we apply this deep neural network? Let's say we have problem, will I pass this class? I have 2 features. Let's start with simple 2 feature model. The first feature is number of lectures you attend. Second feature, hours spent on the final project. This is your data. So these green ones are pass. For pass, those students who has number of lectures this much and number of hours spent on the final project this much passed. Or these students. Okay, these students failed. How can I find if this is going to pass or fail? So we give these inputs. 4 corresponds x1, 5 corresponds x2. Then I should find my weights. Okay, I make prediction. So I need to define loss function here. Is it predicted correctly? The actual one is 1. The loss of our network measures the cost incurred from incorrect prediction. Maybe these weights are not good. That's why I predicted incorrectly. So I need to define the loss function, the actual one. The loss measures the error between the predicted and the actual, the difference between the predicted one and the actual one. Okay, so it's the loss function for all n, for all data points, xi. Okay, the predicted one and the actual one. So this is called objective function or cost function or empirical risk. Both of these terms have same formula. They are same. For example, it is predicted with 0, 1, but the actual value is 1. So it's either 0, either 1. 0 or 1. 0 fails, 1 pass. Okay, although it passed, it predicts as fail. 0.8, okay, it fails, but it predicted as passed. 0.6, it is above 0.5, so it is predicted to be passed. The actual value is passed, so it's correctly classified. There are some loss functions defined. Cross entropy loss. Okay, I will not go into detail, but cross entropy loss can be used for the models that output probability between 0 and 1. Okay, this is the definition of this loss function. There is mean squared loss function. It's the simple loss function you know from regression. By the way, there is also these function names. Okay, also here we can find the slides from MIT. Okay, so this, as I said to you, this is from regression. So f of x has the outcome as continuous values. Okay, it's not like here you see the y values, it's continuous, it's not categorical. Okay, this is used for regression models. It's not categorical, it's not 0 or 1. So for example, this is close to 95, so you can say, okay, the loss here, my prediction and the actual value, the loss that I have is just 10, it's small, but here it's very big. 80 versus 20, 30 versus 90. Okay, so you measure how far is your prediction from the actual value. How we train neural networks. We have loss function I want to minimize, but I don't know the weights. Right, as I said here. Here I don't know the weights. So I should train my network to find out the best weights, like I found the best coefficients for regression. So I want to find the weights. I minimize loss function. Argmin means the best W, the best weights that minimize the loss function. Okay. Here is the picture of the loss function. Okay. Our loss function is a function of network weights. Okay. My loss function has unknowns of the network weights. It's a function of network weights. But it is very difficult in deep neural networks to find the optimal weights because, as you see, it is highly non-convex. so it is really bad. It picks an initial point. In order to solve this optimization problem, okay, as I said earlier, you start with initial points and you iterate until you converge to the point. So it starts with an initial point and it iterates, okay. With gradient descent, it finds the minimum. But as you see, there are other minimal points. These are also local minimums. So there are some problems by stacking on the false local minima. This is the gradient descent, how it converges to the solution. So initialize the weights randomly and it computes the gradient vector, it updates. This is also known as steepest descent in optimization. In steepest descent, this eta, this letter, shows the step length. It shows you how far you should move towards to the next iteration. And this gradient is actually, this minus gradient, is actually the descent direction. So you see that in this example, it was first like this, my initial point. This is my gradient vector to the descent direction. And then it changed the direction like this and it improves it on the next iterations with some step lengths. And in deep learning language, in this terminology, this eta is also called learning rate. Okay, in optimization theory, it's called a step length. This is the TensorFlow codings. This is the gradient. You define the loss, the weights. Okay. How do you compute the gradients? This is a bit detailed about in computing the gradients with backpropagation. It uses chain rule mathematically. Chain rule you know from the calculus. So it uses chain rule to calculate all these gradients. So I will not go into detail. So in practice, how this loss function looks like. This is the loss function looks how it looks like. You see that it's awful. So you don't see, how would you find the optimal point? It's very difficult. So optimizing the gradient descent through the gradient descent, how can we set this learning rate? This is also one more the problem. What should be this learning rate? So with small learning rate, it converts slowly and gets stuck in false local minimum. Okay, this is the optimal one. Initial guess, maybe it falls in a it's stuck in a false local minimum. They may overshoot and become unstable and diverge. So there are ways to find. The first idea is try lots of different learning rates and see what works just right. But of course, this is not possible. The second clever idea, smarter one, design adaptive learning rate that adapts to the landscape. This is smarter. So you adapt this learning rate with some adaptive optimization techniques. These are the adaptive techniques. Adam Optimizer, you may know if you are familiar with deep learning applications. This Adam one is one of the famous one. Also, this Aramis probe is you can try this one. Okay, these are the adaptive optimizers. So these are just the coding parts. I will go to this mini batch part. When you calculate gradient descent, it takes too much. It's costly. Okay, if you have a big data set, it's costly to calculate the gradient for all the training points. Instead, you can pick single data point. This is why it's called stochastic, because just randomly you pick the single data point and you calculate the gradient. But of course, it doesn't reflect the true gradient. Instead, you can use, it's noisy, you can use batch. So you just randomly pick B data points and you calculate the gradient on these B data points. Okay, so it's fast to compute and it's much better to the true gradient. This is very worse. Just finding the gradient on just single data point. It's not close to the real gradient. But if you use B data points, it estimates to the true gradient. When you use mini-batch while training, it gives you more accurate estimation, smoother convergence, and allows larger learning rates. It can parallelize computation, right, and achieve significant speed increase on these GPUs. In practice, neural networks overfits. This is underfitting. The model doesn't have a capacity to fully learn the data. This is the ideal fit, and this is the overfitting. It tries to fit all the points on the training, but whenever you give an unseen data, it will not predict the data correctly. Because it's too complex, it's too flexible. It only fits on the training set. We don't prefer training like this. We don't prefer models like this. In order to compensate this, in order to penalize this, we use regularization technique. In order to regularize complex models, to discourage complex models. As you remember in regression, we have seen regularization. So our regularization here is to drop out some of the connections here. Some of the units, you see, these are dropped out. Randomly, you can randomly drop out these. Typically drop 50% of activations there. Okay. Another regularization is early stopping. You stop training before you have a chance to overfit. So you look at the behavior of your loss function on the training, and then you stop at some place here. Example here. This is the underfitting area, and if you choose something, some model, if you choose the model's complexity on the right region, here right hand side region, if you increase the complexity, then you may have overfitting problems. This is the best, the optimum point to select the complexity, to decide the complexity of the problem. So we have seen the perceptrons, the building blocks, and then we see neural networks, and in training, in practice, we see adaptive learning, batching, regularization for deep learning. We don't have, so I just finished, okay? So that was all for this evening. I hope I could give you the overview of the intuition behind machine learning, the interplay between machine learning, deep learning, and optimization. Thanks for listening.
Thank you, Hocam, for joining us tonight. We have one question, though, that I want to ask you before end the session. It's coming from Berke Kara. He asked, he is studying software engineering right now, and he is taking neural network course, and he is planning to study master in BAU after his graduation. So he asked, he need a help with mathematical side of his topic. Is there any videos or books you can recommend?
He can get into contact with me for the mathematics of neural networks, he asks. I cannot give... He asked the mathematics of neural networks, right? No, he's working on neural networks, but in general, I think he wants to understand the mathematics behind of all these methods.
That's true.
Actually, I'm giving such a course this term. He can listen me, but we are in the middle of the term. I can share, I can add him to my Teams. He can watch my videos, and also I can suggest him a video series of the professors the authors of the books Elements of Statistical Learning. They are from Stanford University. I'm also using those slides of that university, those guys. They also have the videos of the slides. I'm using the slides. I'm in parallel with their slides and their book to make easier, to make students' life easier, having the same book and videos and the lecture slides. So I'm following this. I can suggest him that link. So he can just send me email. I can send him the link, and or whenever he is available, he can also take an appointment and we can talk.
Okay, I guess he can contact you with your school email, right?
Yes. He can send me email, my school email.
I hope Berke is here. I hope Professor answered your question, Berke. Thank you for joining us tonight, Professor. It was productive evening. I hope everyone enjoyed it. Thank you all for joining us.
Thank you very much for inviting me. I hope I didn't bore you with some mathematics. Because I'm a mathematician, I can't allow myself, I can't escape talking about mathematics. But all these methods, all these algorithms comes from mathematics. Their background is math. Sorry if I bored you.
It was good, Professor.
Okay, thanks for listening me.
Thank you, everyone. Have a good night.
Okay, good night.